Misconception when learning symmetry elements and operation among students. The most common are they can't imagine how rotation and reflection because students have experienced difficulty when building and mentally manipulating three-dimensional mental model from two-dimensional objects. Means that students can imagine how the 2D drawing can be translated into a 3D image mental, so they can imagine how the rotation and the reflection works because of it. To tackle this problem, our team have developed a 3D model called polystyrene ball symmetry model, where with the use of this model, students can have a hands-on experience where they can see the rotation much clearer because they can hold the model, and they can see the reflection by observing the model based on the symmetry element that they have. This model is also detachable, means that variety of combination can be done, means that other than other set model, they can also use other elements as a reference and make multiple combination to make sure all the symmetry and elements, they can see that much clearer and know how it's work by rotating it and cutting through it to see the reflections.
There are three components of this symmetry model. The components of the symmetry model are polystyrene ball, plastic straw, and watercolor. The symmetry model have a few interesting features. The first one is detachable. This symmetry model has a detachable design. The bond, which is the straw, can be detachable to the polystyrene ball, which represent the element in the symmetry model. Secondly, the model has a color-coded element. The purpose of the element being color-coded is to distinguish the type of element because there are several different elements in the symmetry model. The colors involved are blue, orange, and green, and each element represents different elements based on the molecule. And the last one is the symmetry model is adjustable. The design is adjustable, allows the model to be customized according to suitability. Before I explain about instruction on how to use this symmetry model, firstly, we must refer the compound used before construct the model. Then, take the central atom, which is represented by blue ball. After that, we can stick the bond on the central atom, which represented by the straws. Next, attach the chlorine atom, which represented by the green ball. Lastly, we have to attach all the remaining iron atom, which represents by the orange balls, to all the balls. As we can see, there are 4 orange balls that are represent the iron. After the symmetry model is completely built, we can identify its symmetry element and its symmetry operation. For the symmetry operation, locate the C1 and C2 axis and rotate 360 degree and 180 degree. As you can see, the C1 and C2 cross the central atom from the chlorine atom to iron atom. After that, we can determine its plane. To determine its plane, you can grab a ruler and put it vertically on the central atom, and you can also put it on the same direction with C1 and C2. The plane that we determine from the model are sigma V and sigma V prime. The symmetry element of this symmetry model is bipyramidal.
Alright, for the compound that we use, firstly we're going to find the symmetry element of the compound. by using this model. Alright, for the green ball, it represents the CL, and the orange ball, it represents the fluorine, and the blue ball represents the XE. So the first step is to determine the rotation of the compound. So as you can see over here, on the top, it looks like this, right? So from the top, it only can be rotated 360 degree, so that the compound, so that the atom stays at the same spot. But as you can see from this side, if you rotate 180 degree, which like this, you get the same symmetry element. So C1, C2 axis on CL, and there is C1, C1 in each fluorine atoms. And now we're going to look at the plane. Alright, in this compound, we identified two vertical plane, two sigma V, which is over here, right over here. It crossed from top part of the compound, which is fluorine atom, until the bottom part of the compound, and it also cross in the middle of Cl and in between two fluorine atom. So it has sigma V. Oh no. Sorry. And this one is actually sigma V prime. It's actually over here, which is it is like that. So it cross the atom in vertically, and also it's over here. The plane is over here, also a vertical line, because the main axis is over here. It goes through Cl atom and in between fluorine. So the plane is actually vertical to the main axis. So over here I put sigma V prime, which indicate the vertical plane. So we can list the symmetry element, which is E, which is equal to C1, and then we have C2, and then we have sigma V and sigma V prime. And the symmetry operation of the compound is C2V. Alright. And the next part is the object that we choose is actually a makeup sponge in the shape of the heart, which interestingly, this object has the same symmetry element as this compound, which is, as you can see, the first step is we're going to find the main axis of this object, which is over here, the main rotation. Right over here, there are C1 and C2, which is if you rotate 180 degree, you get the same symmetry. And also, the plane for this element is also the same, which is over here. We cut across the object vertically. So over here you can see that it has the same it is symmetry. And also we cut across, which is also vertical because the axis, the C2 and C1 axis going through over here, going past through this object over here. So it the second plane it crosses the object like this way. So it has the same symmetry element and also symmetry operation.
In conclusion, the model is detachable and color-coded, help in making students to more understand how rotation and reflection works by using the 3D model. The detachable part allows the student to detach it and make a new type of molecules, while the color-coded helps to distinguish your other element from others. So, we think that our model symmetry is good to help in solving the misconception among the students about the rotational and the plane of reflection, and to imagine on how it rotates and the plane of reflection.